So continuing with our description of the system of particles. So we have, for a system of particles, this relationship, which is nothing but a restatement of the Newton's second law. All right. Now we can write this. I can just simply rearrange and write this as all right. And then if you do an integration on both sides, let's say from a certain time t naught to t, and we assume that the force depends on time. Okay. Then we would get on the right side the final momentum, or the momentum at time t, minus the momentum at time t naught. Okay. And in short, this is equal to the change in momentum. So it's nothing new really. It's just rewriting the Newton's second law. Here it appears is as a in the differential form, or as a differential equation. And here what you have is the integral form of the Newton's second law. And it is useful in the situations where you have a force which depends on time. And what this restatement is telling us is that if you're applying a certain force on an object, it would change its momentum. We see that here as well. But here it has a little bit more detail, in the sense that if the force is time dependent, then it depends, the change in momentum depends on both the magnitude of the force and how long the force was applied. Okay. Again, if it is a uniform force, then this is very simple. So if it is a uniform force, if the force does not change in time, and you applied the force for a time t to from 0 to a certain time capital T, okay, and the force is constant over this interval. A constant force is acting on that. So the change in momentum would be, and if that force is simply F, the change in momentum would be F times, or T times F. And that is nothing but the area under this curve. All right. So it really depends on how big the force is, this side of the rectangle, and how long you applied it for. All right. And in terms of the constant forces, this is very simple. But if the force, let's say, is, think about, if you throw a tennis ball against a wall, okay, what kind of force profile you think of? The force would not be constant in time. The force acting on a tennis ball that hits a wall, for example, is more likely, although it's very hard to know its exact form, and this is just a guess. It's more likely going to look like this. Let's say T0 is when the ball touches the wall, and then force goes to a maximum, then goes to a 0. So this is the contact time. This is the time the ball was in contact with the wall. Okay. And once it's no more in contact with the wall, there is no more force. Okay. Now this area under this curve, the force time curve, would give you the change in momentum. Okay. So there are other examples one can think of, and it's not very common that we use it, and it's not very useful mechanism because we do not know the force dependence on time. Nevertheless, sometimes in collisions, if we want to estimate the average force, all right, if we want to estimate the average force involved in a collision, we can always figure that out. And that is, for example, let's say you have a 1-ton car of mass 1 ton hitting a tree. Okay. And now you assume, of course, you can do experiments to figure that out. Let's say that the time of collision was just 1/10 of a second. And at the time of collision, it was traveling, the car was, let's say, traveling with the speed of 20 meters per second. Now, if you want to estimate what was the average force involved in the collision, okay? What was the average force involved in the collision? So you can calculate F average. Okay, of course, the only, because the force is time dependent in this case as well, and there would be different force that would be acting. We can't figure out the exact profile of the force, but we can find out an average quantity, okay? And that is simply the change in momentum. Of course, after the collision, car comes to rest. So all the momentum goes, so the change in momentum is equal to the momentum of the car. And the momentum of the car is 100 times 20 divided by the time of the collision, 0.1. And then this gives you the average force involved. This turns out to be quite large force. Okay. These estimations are useful if you are looking at safety tests for cars and things like that. Any questions about this? Oh, and by the way, this way of writing Newton's second law, sometimes also referred as impulse momentum theorem. Okay, and this quantity sometimes in literature is referred as the impulse. Okay, J of t, impulse momentum theorem. Any questions about this?
Sir, could you write down the intermediate equation for the integration?
What do you mean by the intermediate equation?
Sir, how did we go to momentum from force? So we replaced it with mv or something like that.
कहाँ पे?
In the integration.
ये
Yes, sir.
ये समझ आ रही है कि क्या है?
Yes,
पहली
sir.
इक्वेशन, ठीक है? तो dt को मैंने इधर लिख दिया है, ठीक है? ये क्या है?
Change in momentum.
Change in momentum, yes, or small change in momentum, right? And if I integrate both sides, so ये हो गया, ठीक है? और ये हो गया. ये अब इंटीग्रेशन किस वेरिएबल के रिस्पेक्ट से है?
Time.
ठीक है, dp यहाँ से देखें ना, ये है विद रिस्पेक्ट टू dp, ठीक है? यहाँ पे टाइम से इंटीग्रेशन है, यहाँ पे dp है, और लेट्स से कि इस साइड पे अब इंटीग्रेशन किस विद रिस्पेक्ट टू व्हाट वेरिएबल टाइम है, t नॉट t. तो इधर लिमिट्स क्या होंगी? इधर लिमिट्स होंगी p एट t नॉट, ठीक है? एंड अपर लिमिट क्या होगी? p एट टाइम t, ठीक है?
ओके
इधर
सर, समझ आ गई.
All right. So now we start with the rocket dynamics. Okay. Because whenever you write Newton's second law, whether you write it in this form or you write it in this form, dp over dt, you're always assuming, even in this case, if you open this integral, it's the same thing, is mv. Okay. And if you were to evaluate this derivative, most likely you would evaluate it to be m dv over dt, right? You wouldn't add any other term. And the assumption here is that the mass is constant with respect to time. And the mass is constant with respect to time. If you did not take the mass constant, then there would be another term. Let me just write it vaguely. Alpha times dm by dt. You see that? You see that? So the assumption in writing the Newton's second law is that mass is constant. Okay. So is it always true? Do we always have systems whose mass is always constant? And someone has the
No.
hands raised. Hasan Ali ji, बताएं.
और मेरा इसके लास्ट में जो आपने क्वेश्चन सवाल है, जब मैथ्स को हम वेरिएबल लेंगे तो जो डीवी ओवर dt के साथ जो m है वो रहेगा या
वो अभी देखते हैं. I'm just trying to motivate this. Okay, let me finish this discussion and then ask again, please, if it is not clear. Okay. All right. So
yes,
the point I'm trying to say is that in Newton's second law, in its simple form, okay, we are always assuming that mass is constant. So the mass is not always constant. And can you remember an example? Do you remember an example? Can you give me an example where mass is not constant? In chat, just type it. No, I'm asking about when the mass of a system is not constant. Do you see any systems?
Sir, electrons.
No.
Sir, relative effects आ जाते हैं ना? The
No,
higher
I'm not
your,
talking about. I'm not talking about relativity yet.
Sir, when one mass splits into two and they both move in different directions.
No, no. Simply, we remember it. We already have the hint. We're talking about rocket dynamics. When a rocket is
It's a-
lifting upwards, you see,
उसका mass change हो रहा है because उसका fuel change हो रहा है.
because it's emitting gases, hot gases. Okay, it's a huge exhaust. So its mass is not constant anymore. All right. So the rocket is losing. Yet losing compartments is another way to lose mass. But rocket is continuously losing mass. Okay, by exhausting the burnt fuel. All right. In a similar way, you have seen conveyor belts. Have you seen conveyor belts? Yes. So the conveyor belts, the mass is also changing in case of a conveyor belt. So you've seen conveyor belts in superstores, right? Which are carrying. So as you're placing things on them, constantly you're changing their mass. All right. So we have in real life systems where mass is constant. Okay. So we must need to work out a better form of Newton's second law or an equation of dynamics in such cases where mass is constant, where we do not assume that mass is, sorry, the mass is variable. All right. So now let's look at a rocket. let me just make a vague picture of a rocket. Okay. And let's say that its total mass is m, all right? And it is moving with velocity v upwards. Okay. And then the rocket may be accelerating. So we cannot be, so we'd be defining all the quantities or all the dynamics with respect to an inertial observer. Okay. Let's say somebody on Earth, okay, looking at this rocket. So this is the speed, the velocity of the rocket as observed by the observer on Earth inertial frame. So at time t, the rocket has a momentum. Let me write it, P of t equals to mv, right? Any difficulty about this? Okay. So for a later consumption, can I also write it like this? Plus dmv minus dmv. Huh? Doesn't change anything, right? Because these two terms just are zero. So that is the momentum of rocket when we start looking at it, the moment we start looking at it. Okay. Let's say at a slightly later time, t plus delta t, we look at the rocket again. By then, the rocket has exhausted gases equal to a mass of dm. This much mass has been exhausted, okay, in terms of the gas exhaust, the fuel for propulsion. Okay. So what is now, let me just rewrite it in a more clear fashion. So this is mass, this is velocity at t, and this is t plus delta t. Now, what is the mass of the rocket? If this much mass has detached or left the rocket in time delta t, so what is the mass of the rocket now? dm minus dm, right? So, and in the meantime, it has also changed its velocity by a small amount dv. Now, this is its velocity. It's not the same anymore. Mass has changed and its velocity has changed. So now what about the emitted gases? Now let's say that the gas was emitted, or this exhaust is emitted at speed u relative to the rocket. Okay, at speed u relative to the rocket. So what would be the V exhaust? Let's say if I want to write V exhaust, if that is V rocket. So for an observer on ground, it would be V plus dV plus U. Okay. Just U, where U is the relative speed of the exhaust with respect to the rocket. So this would be the V exhaust for an observer on ground. All right. And the masses of the exhaust are dm. Okay. Now looking at these two things, can we write now the momentum of the total system? Okay. Momentum of both the rocket and the exhausted gases. Somebody have their hands up. Abdur Rahman.
Yes, sir. Sir, मेरा question ये था कि wouldn't U be the speed of the exhaust at the time at time t plus delta t में U change नहीं हो जाएगा? नहीं, U तो वही रहेगा actually.
बिकॉज टी पे तो टी से पहले जो एग्जॉस्ट है, लेट्स से वो हम सिस्टम का हिस्सा नहीं कंसिडर कर रहे, जितना एग्जॉस्ट टी एंड टी प्लस डेल्टा टी के दरमियान हुआ है उसको कर रहे हैं, ठीक है। एंड लेट्स से दैट द रॉकेट इज इमिटिंग एट कांस्टेंट रेट विद रिस्पेक्ट टू इटसेल्फ, इट्स एग्जॉस्टिंग एट अ कांस्टेंट रेट, ओके, सो यू कैन बी कांस्टेंट, ठीक है।
यस सर, सही है, अंडरस्टैंड। पे उसमें चेंज डीवी सही हो गया, सही हो गया।
All right, now let's write the momentum of the rocket at t plus delta t. Can you help me write this? Okay. What is the mass of rocket now? M minus dm. And what is the speed of rocket now? V plus dv. Okay. That's the momentum of the rocket. Sorry, this is the momentum of the total system, not the momentum. This is the momentum of the rocket. Okay. So both these momenta are the momentum of everything. The exhaust included when it was part of the rocket and when it has been exhausted. So now I'm expanding the definition of the system, okay? So this is the boundary of the system. Whether the exhaust were part of the rocket or it has been exhausted, that still remains my total system, okay? And this momentum has that everything in, and this momentum also has everything in. So this would be now the momentum of the rocket, but I also have to write the momentum of the exhaust, and that would be dm times the speed of exhaust or the velocity, v plus dv plus u.
सर आपने ऊपर वाली इक्वेशन में प्लस डीएमवी और माइनस डीएमवी दोनों किया हुआ है और आपने इसमें सिर्फ माइनस डीएमवी किया।
किसको?
ये जो पहली वाली इक्वेशन थी मोमेंटम की, उसमें आपने प्लस डीएमवी एंड माइनस डीएमवी दोनों ऐड किए हुए हैं ना?
ठीक है,
लेकिन सेकंड वाली में आपने सिर्फ माइनस डीएमवी वाली टर्म एंटर किया, प्लस डीएमवी वाली तो की नहीं है।
अच्छा देखें, अच्छा देखें, ये देखें, ये तो मोमेंटम है मेरा एक्चुअली
जी
टोटल, ठीक है। ये तो मैंने
जी,
कन्वीनियंस के लिए टर्म्स खुद डाली हैं ना,
सही हो गया।
ठीक है। लेकिन मैंने यहाँ ऐसा कुछ नहीं किया, ये सारी टर्म्स आ रही हैं सामने, उस सिस्टम को देखें तो,
सही, तो
ठीक है।
आपने बेसिकली रॉकेट की मोमेंटम से एग्जॉस्ट के मोमेंटम को माइनस किया।
हाँ, क्योंकि दोनों ऑपोजिट डायरेक्शन में है,
सही है,
ठीक है।
सही
तो
तो
टोटल मोमेंटम यही होगा ना,
बिल्कुल।
ठीक है। ये रॉकेट का मोमेंटम है, ये एग्जॉस्ट का मोमेंटम है, ठीक है। नाउ व्हाट इज द चेंज इन मोमेंटम? डेल्टा p during this time interval, and that would be p t plus delta t minus pt. Okay, can you quickly do this calculation? So what is the answer? No one has been able to figure out. Okay, then you can check against this. mdv minus u dm, ठीक है, राइट। Okay, now let's divide the whole equation by delta T. Okay. Okay, and then take the limit delta T very, very small. Or delta T going to 0. And this equation becomes dP over dt m dV over dt. Okay, and minus u dm dt. All right, is this clear, everyone? All right, so what is this?
Force.
Force, the external force. External force is equal to mdv dt minus u dm dt. And this is the rocket equation, the most basic form of the rocket equation. Okay, this is the fundamental equation when you're dealing with systems which involve variable mass. Yes, Rafe?
सर हम dv और dt की जगह a लिख सकते हैं एक्सेलरेशन वाला.
हाँ जी, लिख सकते हैं.
ओके तो सर ये वो f is equal to m a. ओके ठीक है.
ठीक है, बिल्कुल लिख सकते हैं. और ये देखें कि बेसिकली ये देखें कि ये जो एडिशनल टर्म आ गई है, दिस इज दिस, if the exhaust velocity is 0, then what would you get?
f is equal to ma.
So you recover the Newton's second law. So this is more general in that sense. It's more general than the simple Newton's second law, right? One
Sir,
thing.
one more.
Or
Sir,
if so either the exhaust velocity is 0 or the mass is not changing, then you get what? Newton's second law in both cases. Right? But secondly, it's very interesting. If you write the Newton's second law like this for a rocket, now if the rocket is, if you are exerting this much force, the rocket gives you this, so the rocket has this much acceleration. If you were doing something externally, by exhausting, the rocket accelerates faster than it takes smaller force, because now you have m dv over dt minus this term. Okay, now the rocket can accelerate at the same rate with a relatively smaller force. Okay, we will do an example and this would make sense how changing mass actually contributes to different acceleration or different force, or you require different force. If you have the same acceleration, then you would need a different force if you have this additional term. Yes, we will have a real life example. Any questions so far?
Sir, मुझे जो equation मिला था वो थोड़ा फर्क था. I have m dv minus 2v dm minus 2d square mv minus u dm.
Okay, check again. I think you may have missed the symbol somewhere. देखें ये आपकी टर्म्स हैं m v एक टर्म है, इसके साथ कैंसिल हो जाती है. Then you have m dv टर्म, ठीक है, इसके साथ माइनस है. जब आप सब्ट्रैक्ट करेंगे तो ये साइंस चेंज हो जाएंगी यहाँ पे, ठीक है. So this term cancels with this term. This term cancels with dmv. This is minus and dmv.
I think -2 d square mv फिर भी रहेगा.
And all the terms get cancelled. So you have this minus dmv, this cancels with this term, all right. And then you have dmv, ये उसके साथ cancel हो जाएगा, ठीक है. And then you have dmdv, that cancels with this dmdv, all right. So only you will have
Like both the
dmu term here.
dmdv's have a negative sign.
जी सर ये ऐड हो रहे हैं, मेरे पास भी यही इक्वेशन आ रही है जो इसकी.
Sir, because both the dmdv's have a negative sign.
Which dm, so you have an additional term, so probably there is a sign mistake somewhere. Okay, they should cancel. Let me see. M minus dm v plus dv minus v plus
Sir, will it be m? Actually, नहीं वो नहीं हो सकता.
okay, just figure out there is a symbol problem somewhere. Okay, or a problem of sign somewhere. I don't see it. You can figure that out, I'm sure. M minus dm v plus dv minus dm come on, dmdv dmu dmv. Maybe I think we may have I think this might be positive. Okay, so then if you check, then does it make sense now, or it's still a problem?
Sir, what will be positive?
This term here.
Or
ये हम
sir,
class-
will it be m plus dm, because dm's value will be negative because the change in mass is decreasing. So can we write it as m plus dm?
Um,
सही हम क्लास के बाद में कर लें शुरू से एंड तक मतलब अभी हम आगे चलते हैं.
all right. Yeah. So just I don't know. There is a problem with the sign. So just check in the notes and you would have the correct expression. Okay. So once more. Dm by dt. All right. So the point is that if you know the rate of change of mass, and that is not very difficult to find, okay? Because you know, I mean, in rockets, for example, in real rockets, you know at what rate are you going to exhaust, okay? You can also have sensors, or there are ways on board you can figure out the relative velocity of the exhaust with respect to the as absorbed from the rocket. All right. So and if you know,
cameras are out of focus हुआ हुआ है.
sorry.
Cameras were out of focus हुआ हुआ है.
Maybe because I'm moving.
सर एक दफा कैमरे के आगे आए वो सही हो जाएगा. एक सेंटर में आए पता नहीं आउट ऑफ फोकस हो गया. हो गया सर सही.
So if you know, and we know that, for example, the exhaust speed, the rate of change of the mass of rocket, and the forces acting on it, we can figure out the v as a function of time of the rocket. And we can also figure out x, or in 3D, the position vector of the rocket as a function of time. And we can predict the trajectory, okay? For example, if you are in deep space where the external force is 0, nothing acting on the rocket, okay? So then you will have an equation. You just plug in this value. So you will have an equation that looks like this. dv equals u dm over m. Okay. And now if you integrate on both sides, okay, 0 to t, and here m naught to m. Okay, let's say m naught is the mass when you started observing the system, and m is the mass when you at time t, right? So on this side you would get vt minus v0, and on this side you will get u m over m naught. Okay, so this would be, this is the initial velocity that you, when you started observing the system. So that would be simply u. But do not confuse this u with that u. So that is the relative speed of exhaust, and this is the initial speed of the rocket. Right? If you were working near Earth, for example, then you would have gravity, and then the rest of the equation would be like this. dt minus u dm over dt. Okay. Now Earth is pulling downwards. Okay. So you have to, that is the force that the rocket must counteract to accelerate upwards. All right. So again, if the exhaust speed is 0, or the rate of the change of the system is 0, then you will just get the acceleration equal to, if that's the only force acting. Okay. And you see that if you are exerting a force equal to the weight of the rocket, you would be accelerating a little faster than what you would be doing without this. Okay. So now let's do a more realistic example. Any questions so far?
सर जो आपने इसको mg के साथ इक्वेट किया, मास लेकिन चेंज हो रहा है, तो हम उसको भी हम चेंज नहीं फैक्टर इन करेंगे mg के अंदर मास का चेंज?
हाँ देखिए, ये तो टोटल सिस्टम पे फोर्स लग रही है ना, उसमें वो एग्जॉस्ट भी शामिल है. ठीक है,
Okay, yes.
ठीक है। तो ये कैपिटल M है, ये तो फोर्स है, एक्सटर्नल फोर्स है। ठीक है, okay. Now a real life example. If you've ever been to a jeweler's shop, you may have actually seen this happening, that if you, let's say, this is a weighing scale, right? And now you're dropping a chain. I'm sorry, it should be straight up. Okay, you're dropping a chain of length L. Okay, and the total mass of the chain is M. All right. So you're dropping the chain into the scale to actually check its mass, check its weight, for example. All right. So at the observation time, before the observation time, t much t less than t. Okay, what would be the reading on the scale? The chain is
0.
not touching. Okay, the reading on the scale would be 0. And what would be the reading on the scale after T2? Let's say it takes time from T1 to T2 to fall all the chain into the, and then you have enough time, okay? So a few seconds later, what would be the reading on the scale?
M हो जाएगी सर।
And the reading on the scale would be M. Now the question is, for such a system, that you leave the chain, okay? Once its lower end is touching the scale, you just release the chain from the upper end, right? The question is, what would be the reading on the scale when chain has fallen an X length? All right. So that is something that we need to figure out. What do we expect the reading to be between 0 and M? What would be the reading? Any guesses?
So I think
A
weight
fraction of M.
ऐसा increase करेगा as the मतलब length increases तो mass भी increase करेगा.
It will be a
हाँ, लेकिन
fraction of M.
it would be a fraction of M. Who is that? Amina, right?
Yes, sir.
Yeah, that's the common sense, right? You see, that it cannot be larger than M, right? Because that's the total mass, and by dropping X length means we have only partially dropped the chain, right? So let's try to figure out using answer to this question using something that we just developed. Okay,
सर इससे ज्यादा नहीं होगा बिकॉज वो गिर रही है तो इसी
let's see.
फोर्स
Okay, let's find out the answer. Eh? Okay, so before anything, this is a problem of free fall, right? So the free fall v squared minus, for free fall we have this equation, right? Equals 2gx, यही है कि पूरी चेन के लिए तो इनिशियल स्पीड हम 0 ले लेते हैं, तो v क्या होगा? स्क्वायर रूट 2gx, something that we are going to use later on. Okay, now separately, let's say that this chain is of uniform mass distribution. Okay, uniform mass distribution. So let's say, and what is the mass in one small dx length of the chain. If it is of uniform distribution, the mass in length dx would be simply m over L. This in a way is a linear mass density. Okay? Divided all the mass over all the length. Okay? And once I have divided this, then I can calculate the mass of any patch of the chain. That's the purpose of defining densities. Very useful. Okay. By dividing the total mass by total length, and I can only divide this. I can only make this or say that this is the density because if I know that the chain has uniform mass distribution. So it's not thick somewhere and thin somewhere. It's a uniformly crafted chain. So
Sir,
then if you
will it multiply with dx?
no, that would be, so this is I'm saying this is not the mass, this is the density, mass per unit length. And then
Okay,
if you multiply it with dx, that would be a small mass dm. And if you're not convinced, if you multiply it with L, you will get M. Okay? So that means that this quantity is actually density. So now let's say the chain falls only by distance delta x. Okay? Delta x. What is the change in momentum of all the chain from here? Everything is falling with the same speed. Parts of bits of chain, the chain itself, it's a free fall problem. No other force is involved. Okay. So the chain, so the momentum dp or dp, this much momentum would change of the chain dm by v. If the chain has fallen this length only. Now this much momentum of the chain has changed. Okay. Okay, sorry, before I solve this problem, let me convince you what do we have to actually find out. What is the reading on the scale is, usually these scales are designed to do this. The normal force divided by G. Okay. All these vertically weighing scales, they're designed to do this. So whatever the normal force that this scale is exerting upwards, divided by G is the reading on the scale. And the normal force we know would be exactly equal to the weight, okay, of the object that is lying inside the scale. That would be the force that the chain is exerting on the scale at any time. When it is not in contact, there is zero force that the chain is exerting on the scale. So normal force is zero, reading is zero. And when it is peacefully lying in the scale, the normal force is exactly equal to mass times the gravitational acceleration. So you plug in here mg, that's the normal force, and the reading becomes simply m. So what we are looking for in between situation is this thing, the normal force over g, and we know that the normal force is the force exerted by the chain on the scale divided by g. So in this exercise that we are just starting, what we need to figure out is the force that the chain would exert on the scale from the point of release to until it has dropped by a distance x or by a length x. All right. So this is dp. That's a change in momentum when chain has only dropped by a small length delta x. Let's divide it by dt on both sides. Right. And we know what dm is. M, L, all constants. V is also, and then we get dx by dt. Okay. So dp by dt is equal to, and this is what? Velocity. So then this becomes mv squared over L. That is the change in momentum when a small portion of chain has dropped on the scale. That is the change in the momentum of the chain. Okay. And we know that this is force because it's dp over dt. So the chain exerts this force on the scale. All right. This is it's exerting constantly. Is a uniform force. It does not depend on time. Okay. Constantly exerting as it is dropping. Okay. As it is dropping on the scale, it's exerting this force. But let's see by distance, when the chain has dropped a distance x, if this much length is already in the scale, okay, and sitting there, the rest is falling, but x distance has already fallen this much length. How much mass is already in the scale? M over L times x. Isn't it already in the scale, this much mass? Right? And then if you multiply it with g, that is the weight of the length of the chain, so the x length of the chain. That is also the force that the chain is exerting on the scale. So it's exerting two forces. This force, Wx, and this force due to the rate of change of momentum, and this force that is already, that chain is already sitting together, okay, sitting inside. Now let's add them together. So you get mv square over L, this force plus mgx over L. All right. That is the total force Fc, the force that we are looking for. Okay. Once we know this, dividing it by g would give us the reading on the scale. Okay. And we know what is the value of v here. V here, 2gx. Let's bring them down. And this becomes 2mgx over L plus mgx over L Fc. Okay. And then this becomes simply 3mgx over L equals Fc. And the reading on the scale would be Fc over G 3mx over L. First, let me know if you're not convinced before we look at it a little bit more. Does it make sense? No? But we'll plug in real numbers and see what this number looks like, okay? If you're trying to, but just let me know if you're not convinced that with the symbolic relationship, okay? If any logical gaps that needs to be bridged. All is good?
Sir, can you please explain how you went from v square to 2gx?
ये जो इसके ऊपर इक्वेशन लिखी हुई है ये देखें ना, v
Oh,
स्क्वायर,
okay, yes.
तो ये v is equal to square root 2gx है, तो यहाँ पे v स्क्वायर की वैल्यू प्लग
Okay.
की है.
Thank you.
ठीक
Sir, I
है.
wanted to ask the constant force mv square upon L that is always being exerted on the scale. Where is that coming from? Is that coming from the kinetic energy of the chain?
कौन सी force?
mv square upon L.
Yes, yes, it is coming from the change of momentum, because this mass is coming down with a finite speed, velocity, but it has been brought to rest. It is being brought to rest. What is bringing it to rest? The normal force. Okay, so the change in momentum, the scale must exert a force upwards to affect this change in momentum. Yes, it is coming from, in a way, kinetic energy, or from here you see this is coming. So it has a finite kinetic energy, or in other words, it has a finite velocity. And this, to stop the chain, so the scale must exert two forces. Whatever amount has already landed on the scale, the weight of that normal force, and it hasn't completely landed. So it's some way through, is the ratio between x and L. When x would be L, then this would be mg, yeah? The total weight when it has landed, or whatever, however much mass has already landed in the scale, that portion. And this portion is, this contribution is coming from the normal force that its scale is exerting to slow down and bring it to zero speed. Every little piece of mass that is coming in time. ठीक है? Okay, now let's look at this equation. So let me just rewrite mv squared over L plus, or even in a more mx over L, and also a simplified version of this, C over G is equal to 3m x over L. Okay. So first, let's look at the first equation. Okay. Let's say that the chain has fallen, okay, which means this V has become 0. So no more V, eh? It's not moving anymore. All the chain is already in the scale. So this term goes to 0. Okay. And if it has already fallen, then x is already equal to L. Right? Now this would become simply M. ठीक है? Okay, now let's analyze this. Go to M. So that would be the reading. Okay? And of course, initially, if it is not touching, then there is no normal force. The normal force is a contact force. So this would be, the reading would be 0. So let's say that you have a chain of length 3 meters. Okay. And it has fallen only by half a meter, or in other words, 1/6 of the total length. Okay. Let's plug those numbers in here. What do we get? What would be the reading? Anyone? Is it that difficult? Hmm?
So 0.5 MR.
Yes, that's correct. Because ये 3 meters है, 3 cancels, and this is half m. ये जवाब आ रहा है ना? Right?
Yes sir, ये आ रहा है.
लेकिन यार इस तरफ देखें, इधर क्या हो रहा है? 3 मीटर की चेन है, कितनी ड्रॉप हुई है?
1/6 ड्रॉप हुई है सर।
अभी 1/6 ड्रॉप हुई है। मैथ कितना अपीयर हो रहा है स्केल पे?
हाँ, 3
हाफ।
times the
ठीक है, isn't it counterintuitive against common sense? Okay, so this would be half m. अच्छा, अब let's say कि the same chain it has dropped by a distance 1 meter, ठीक है, which is 1/3 of the length. Only 1/3 of the chain has fallen, has dropped. अब mass कितना आएगा?
m आ रहा है सर,
Hmm?
m आ रहा है।
M's.
M. So while the chain, only 1/3 of the chain is in the scale, only 1/3, and the scale shows M. Okay. Okay, so next, let's say that now the chain has just finished dropping. So X is 3, just finished dropping. Okay. अब कितना आएगा?
3m हो जाएगा सर।
3m. See, 3 times larger than the mass, actual mass, the scale would show. That is an advice if you are going to buy something expensive at jeweler's shop, a diamond or something of gold. So let the scale come to rest completely. Otherwise, okay. So you see that because of the chain has to exert additional force to bring the scale to bring the chain to rest. So the reading on the scale is larger than 3 times, at maximum can go to 3 times larger than the mass of the scale. But once it comes to rest completely, then if you go back to this equation and set the V to 0 and X to L, then the scale would restore back. Okay? So it would show larger mass up to the right, like right to the end of the process of falling. And then once it has done falling and it has come to complete rest, then the scale would show M again. Okay? Suddenly, quite suddenly, because V immediately goes to 0. Okay, that's all that I have for today. Okay, thank you very
One
much.
quick question.
And if you have any questions, I'd be happy to take them now.